Okay, so the next part that we have here is called analysis of frequency distributions. It's called analysis of frequency distributions. And what that's about is that basically, suppose that you have, for example, some data over here. So, for example, you have some data related to, for example, the heights of, heights of a number of people. So you have your data in this way. You have the height, for example, in centimeter, and here you have the number of people. You have the number of people. So, for example, let's say that the height, for example, was 150, and the number of people who had this height, the number of them was, for example, I don't know, for example, 5 people. 155, for example, 6 people. 165, for example, 3 people. 173, for example, 2 people. 178, for example, 8 people. And so on and so forth. So suppose that this is your data. Now, with this data, basically what happens is that, for example, suppose that you calculate for example, basically the measures of dispersion of data that we had, we had a couple of things here. Let me see what we had. So we had the step deviation method, mean method, no. We had the standard deviation, for example. We had the standard deviation, which was basically a measure of, for example, which was basically some measure of dispersion. Some measure of dispersion of basically your data. And we also had, for example, we had the standard deviation. Standard deviation, we had the variance. We had the variance, and also I think that was it. So we had also something else called we had some other measure which we measured about we had basically some sort of mean deviation about the mean, about the median, and we had the mean deviation about the mean. So we had basically these 4 basically measures of, basically we had this measure over here, which was standard deviation. This was variance. This was the mean deviation about the mean, and this was the mean deviation about the median, and this was the mean deviation about the mean. So we talked about these 2, and we came to the conclusion that these 2 were not basically good measures of dispersion of data, and then we came up with these 2, right? We came up with standard deviation and also with variance. Now one of the characteristics of, let's now forget about mean deviation, and let's talk about basically variance and standard deviation. Now we said that variance was basically sigma squared, which was basically sigma of f of I, for example, times x of I minus x bar whole squared as I goes from 1 to n over sigma of f of I as I goes from 1 to n. And that was basically the mean of basically the square of the distances of every observation from the mean of the data. And then if you take the square root of this, which will give you basically sigma, that was called so this was called variance. This was called variance, and this was called basically standard deviation. Standard deviation. Now, as you can see, basically what happens here, for example, when you calculate variance for some data, what happens is that you have your observations here, and you basically subtract the mean of basically your data from each of your observations, and then you calculate the frequency of those observations by this expression, and then you divide it by the total number of observations. So the unit over here is really basically decided or determined by your observations, or by the mean of your observation, both of which are, for example, in this case would be the height, for example, in centimeters. And if your height was, for example, the height in, for example, meters, then you would have, for example, something like this here, and the unit of basically sigma squared would be the height in meters, or the unit would simply be meters, right? Now, if you had, for example, your data for example, if you had the data of, for example, if you had some data about, for example, over here you had country, and over here you had, for example, the number of people, for example. So then over here you are measuring, for example, the population of some countries. And the population of some countries, for example, here you have different countries, and here you have different populations, and here the unit is most probably, for example, head. I think in population, and that sort of thing, they say they usually measure the number of people by head. For example, they say, for example, I don't know, 5, 10, 50 million, for example, heads, for example, or something like that. I'm not sure about this, but it must have a unit, basically. Or if you had, for example, some country, and, for example, over here the area of that country, in square kilometers, for example, then the unit over here would be square kilometers. Then the unit over here would be only centimeters. Now suppose that, for example, I calculated, for example, the variance for this data. I calculate the variance for this data, and I calculate the variance for this data. So over here the unit is centimeter, over here the unit is square kilometer. And of course you know that basically variance, or sigma squared, is some measure of dispersion of data, meaning that you want to basically calculate how your data is basically dispersed, or basically a measure of dispersion of your data, how your data is basically scattered all around the mean of your data, right? So then logically you could not basically compare the dispersion of this data with this data, because over here the unit is centimeters, over here the unit is square kilometers. So for example, this dispersion over here tells me that the dispersion is, for example, I don't know, 125, for example, centimeters, and over here, using the same formula, it tells me that the dispersion or the variance is, for example, 115, for example, square kilometers. Now you have 115 square kilometers and you have 125 centimeters. Now this is a unit of length. This is a unit of length, and this is a unit of area. This is a unit of area. So area and length, you cannot compare them together. Suppose that, for example, it says you want to, for example, compare, for example, apples and oranges. Apples and oranges. And for example, I don't know, for example, you could ask somebody or try to answer this question. Is 2 apples better or 3 oranges? Which one is better? Is 2 apples or 3, basically we have 2 apples and 3 oranges. Which one is better? Or which one is more? Or which one is less? You cannot say that 2 apples is more than 3 oranges because these are apples, these are oranges. Now, of course, basically the idea of better is not very fitting here. But suppose that, for example, I ask you this question. For example, 2 apples I have here, and I have 3 oranges here, and I ask you to use either of these 2 signs, greater than or less than, to basically to say whether 2 apples is greater than 3 oranges or 3 oranges is greater than 2 apples. You cannot decide. But if I ask you basically 2 fruits and 3 fruits here, and 3 fruits here, of course then you can decide that 3 fruits is more than 2 fruits. That you can do. But this one you cannot do, simply because here the unit is apples, here the unit is oranges. And we have the same problem here. The problem here is that the unit here is square kilometers, here the unit is centimeters. So then you cannot simply decide, okay, so now what am I supposed to do with the data that I have here? Here I have 115 square kilometers, here I have 125 centimeters. So which dispersion is more, which dispersion is less? You cannot decide. So what you need to do is that you need to have a way to get rid of these units so that the only thing that remains is the magnitude of the number, the scalar part of the number, so that then you can compare them and decide in which case basically the dispersion is more. And that's exactly what we want to do here in this basically in this part, which has been called analysis of frequency distributions. You want to analyze them. Oh, I had all of this space up here. Okay. So now it says that in earlier sections we have studied about some types of measures of dispersion. The mean deviation was the mean deviation about the mean, and the mean deviation about the this is the mean deviation about the mean, this is the mean deviation about the median. These are the mean deviations. These are the mean deviations. So the mean deviation and the standard deviation, so when we decided that this was not a good way of studying things, and then we came up with the standard deviation. Standard deviation. And as a part of this, we also talked about variance, which is another name for standard deviation. So the mean deviation and the standard deviation have the same units in which the data are given, and I showed you what is meant by that, which is basically these are the standard deviation and mean deviation have the same units in which the data are given. Whenever we want to compare the variability of two series with same mean, suppose that, for example, you have two series with the same mean. Of course, it's important that the mean with the same mean. It's important that the mean or x bar of your data is the same. Otherwise, it doesn't make any sense to compare them, because those measures of variability or those measures of dispersion are all numbers with respect to the mean of the data. And if the mean of the two series are not the same, then of course it doesn't make any sense to do it. But in case you have the same means for the two series, then of course you can compare them. Now, but of course, provided that they have the same units, or if they don't have, meaning that basically in two cases you can compare. First of all, they have the same mean. This condition has to be met, or this condition has to be fulfilled. Otherwise, the comparison doesn't make any logical sense. The second thing is that the two series must have the same units, or basically the two series must both be unitless. If both of them are unitless, or if both of them have the same units, then you can compare them, provided that they have the same mean. So whenever we want to compare the variability of two series with the same mean, which are measured in different units, we do not merely calculate the measures of dispersion, but we require such measures which are independent of the units. And the measure of variability, which is independent of units, is called coefficient of variation, or short as CV. So then you can say that the measure of variability, the measure of variability which is independent of units, is called coefficient of variation. Is called coefficient of variation, or in short, it's called basically CV, coefficient of variation. So coefficient of variation. So coefficient of variation is the measure of variability which is independent of units. Now they have basically defined a coefficient of variation. They have defined it as follows. So the coefficient of variation, they have defined it as basically sigma, which is your standard deviation, divided by x bar, which is the mean of the data, times 100. So that is basically standard deviation. That is standard deviation divided by the mean of the data times 100. Where sigma and x bar are the standard deviation and mean of the data. So that's basically the whole story there. Okay, so then we have basically, for comparing the variability or dispersion of two series, we calculate the coefficient of variance. The coefficient of variance of each series. The series having greater coefficient of variance is said to be more variable than the other. And the series having basically less coefficient of a basically smaller value of coefficient of variance is said to be more consistent than the other. So meaning that basically the larger that this number is, the coefficient of variance, the larger that this number is, we say that basically that the series is more variable than the other. We say that the series, for example, that the series is more variable than the other. That is basically assuming that, for example, the coefficient of variance, so this is basically called the coefficient of variance. So C and V. So if the coefficient of variance of a series, basically you're comparing two series, you calculate the coefficient of variance of one series and the other series. If the coefficient of variance is larger, the number is larger than the coefficient of variance of the other series, you say that the series with the higher basically value of coefficient of variance is more variable than the other series. And the series having lesser or having a smaller number for the coefficient of variance is said to be, on the other hand, you said to be that the series is more consistent than the other. So that's basically the terminology that we use. Now, there is some part over here which is also connected to this part, which we will do in this video, and that is comparison of two frequency distributions, which is basically for comparison of two frequency distributions with the same mean, same mean. So we said that basically the two series that you want to compare, they actually have to have the same mean, otherwise it doesn't make any sense to compare them together, because the number that you get for the number that you get for example, as your sigma or your x bar and so on and so forth, that is basically that number is basically relevant to some mean. And if those means are different, meaning that, for example, you have a series over here, you calculate, for example, I don't know, for example, you calculate for example, we said that basically the measures of dispersion, the measure of dispersion of, for example, of some series, dispersion of some series is measured with, for example, is measured, for example, with, for example, the standard deviation. The standard deviation, for example. Now, the standard deviation is nothing but basically how all of, for example, if this is the mean of your data, actually this is the median. If this is the mean of your data, or x bar, the standard deviation is basically a way of showing you how basically all of these observations are scattered around your mean. So these all of basically for basically the standard deviation, if I call it, for example, sigma, this sigma, the value of this sigma is some number that shows how basically these observations are scattered around some mean related to this data. Now, suppose that you have another series, and in this series, basically the mean is, and suppose that, for example, the unit over here, the unit used for this particular study is in centimeters. And I have another series, I happen to have another series, for example, something like this, and the unit over here is again the same unit, centimeters. Now, the x bar over here is equal to A, and the x bar over here is equal to B. Some other x bar, for example, this is equal to 100, this is equal to 80, for example. And you have all of these observations around your mean, and you will get some value of sigma over here. Now, this value of sigma is basically some number that shows basically how these observations are scattered around this x bar, which is equal to A, right? Now, this sigma is a number that shows how all of these observations are scattered around this x bar, which is equal to B. And so based on this situation, you can see that even if the units are the same, meaning that the units over here is centimeter and the unit over here is also centimeter, even in that case, it doesn't make any sense to compare these two sigmas. These two sigmas, you don't compare them together, because these two sigmas are relevant to two different means, to two different values of mean. So it doesn't make any difference to do that. Doesn't make any sense to do that. Now, in case basically you have the same mean, so what we can do now is that basically, in case you do have the same mean, meaning that in both of these cases x bar is equal to a, and over here also x bar is equal to a, the same values of mean both of these two series they do have. Now, in case they have the same mean, so now I don't care what these units are. I basically somehow get rid of these two units. I get rid of the unit from here. Also, I get rid of the unit from here, and then I will have some measure which has been called the coefficient of variance. Coefficient of variance. Coefficient of variance. And this coefficient of variance is independent of any units. It is independent of any units. And then I can compare the two CVs, or coefficient of variances, with one another, and then come up with some conclusion that, for example, this series is basically more variable than the other series, or the series is more consistent than the other series. That's basically how it functions. Now, with that understanding, now let's see what we can do in order to compare two series with the same mean. We can compare two series with the same mean. So now let x1 bar, and sigma 1 and sigma 1 be the mean and standard deviation of the first distribution. Be the mean and standard deviation of the first distribution. And x2 bar and sigma 2 be the mean and standard deviation of the second distribution. Be the mean and standard deviation of the second distribution. Then basically the coefficient of variance, then you can say that the coefficient of variance of the first distribution of the first distribution, you can call it, we said that we defined the coefficient of variance as basically sigma over x bar times 100. So I can write over here basically sigma, I can write over here sigma 1 over x of 1 bar times 100. And by the same logic, I can say that the coefficient of variance of the second distribution is equal to basically sigma 2 over x of 2 bar times 100. Now, and also we have basically as a given that basically x of 1 bar is equal to x of 2 bar is equal to some x bar, for example. Say means that let's say that it's equal to some x bar, meaning that the means of the two distributions are equal. Therefore the coefficient of variance of the first distribution is equal to sigma 1 by, therefore the coefficient of variance of the first distribution is equal to, I can, instead of basically, I can write basically sigma 1, but instead of x of 1 bar, I can write x of x bar times 100. And also I can write the coefficient of variance of the second distribution is, I can write it as sigma 2 over x bar times 100. Meaning that instead of x of 1 bar or x of 2 bar, I can simply write x bar. Now if I call this, for example, number 1, and if I call this number 2, whatever you want to call it, equation number 1 and 2. Now from basically 1 and 2, you can see that the two coefficients of variation can be compared on the basis of the values of sigma 1 and sigma 2. Meaning that everything else is the same in these two coefficients of variance. The only thing that's different is basically the values of sigma. This is sigma 1 and this is sigma 2. So then you can say that basically for the two series with equal means, the series since the sigmas are in the numerator, the larger the value of the sigma, the higher the value of the coefficient of variance. And the lower the value of the sigma, the lower is going to be the value of the coefficient of variance. So then you can say that for two series with equal means, meaning that if they have basically the mean for both of them are x bar, for example, or any other mean for that matter, but they have to be equal, of course. The series with greater standard deviation or variance, so this is basically the standard deviation or variance, we can take it as, for example, sigma squared, or you can take it as or variance, they have taken it. Probably you can, there might be even, I don't know, but there could be two definitions, meaning that instead of standard deviation, you could also use, for example, variance, which is basically sigma squared. But I don't see it over here, so it says that basically thus we say that for two series with equal means, the series with greater standard deviation, let's take it as standard deviation for now, greater standard deviation is called more variable or dispersed than the other, meaning that the higher the, basically in whichever one, if sigma 1, for example, if sigma 1 is greater than, for example, sigma 2, then you call this number 1, then you call it more variable or dispersed than the other, because sigma 1 is greater than sigma 2. Then you call this series or this first distribution more dispersed or variable. More variable or dispersed. Dispersed. That's it. It's an unusual word. Also the series with lesser value of standard deviation or variance is said to be more consistent than the other. And then in the same situation too, we can call it more consistent, because the variability is lower there. So you can call it more consistent than the other one, of course, compared to the other one. Now let's take a couple of examples and see basically how we can use this idea for different situations. We have a couple of basically examples, example 13, 14, 15. That's basically all the examples that we have, but they will take up at least probably half an hour or so. So we will talk about those in the next video. I think that's enough for now. So I'll see you in the next video. Thank you.